Okay, cool. So we have functions today and function notation. So a function is just another way to represent an equation. So before we actually start computing stuff, let's look at the definition of a function, right? So a function, to be a function, means that every x in the domain, every x in the domain, meaning every x value that's on the x-axis, has at least one y value, or has only, not at least, has only one y value. Every x in the domain has only one y value in the range. I'll put y value in the range. So I'll even put this up here, every x value. So every x value in the domain has to have only one y value in the range. Now that may not mean much to you right now because it's just a definition, but I can show, for example. So here we have a blob. This is my domain. And over here, another blob. This is my range. Now let's say in my domain, I have x value 1, x value 2, x value 3, and in my range, y value 1, y value 2, y value 3. Now, in order to be a function, every x must have one y value in the range. That is the basic definition of a function. Every x value must have one y value in the range. Okay. So another thing about functions is, again, I said it's another way to represent an equation. So an equation would look something like this, something that we're used to. Y equals mx plus b. A function is going to look very similar, except now you replace y with f of x. We say f of x equal to mx plus b. So all this is doing is taking y and putting it as a function notation. Just know that they both mean the same thing. So y is equal to f of x. They are the same exact thing. And again, the way you say this notation is you say f of x, or f at x. It's the values of f, or you can even say the values of y at x. Every x has a y, and every y depends on an x. So x is always the independent variable. I'll write that down too. X is always the independent variable, and y is always dependent, because y always depends on x. There you go. So just a brief definition of what a function is, because we will get into computing functions, but it's also good to know, well, what is a function? Why are we doing this? And it is just another way to state an equation. And you can label functions whatever you want. F of x, R of x, B of x, whatever letter you choose. Okay, so that's the definition of a function. Okay, so now on our page, it says use f of x equals 9x minus 5 to answer the following. For each question, state whether you are given the input or the output. Okay, so for number 1, it says evaluate f of -3. So this is f of -3. Remember, the value inside the parentheses is your x value. It's always your x value. So for this question, we are given an input. And what we're going to do is input that x into the function above and evaluate. And what evaluate means is to simplify. We are going to use whatever order of operations and simplify. So this is an input. Okay, so now let's check it out. F of -3 means we take -3 and we plug it in for that x value in the function given above. So we have 9 times -3 minus 5. We have substituted that value in. We have input that x value. And now we just simplify. 9 times -3 is -27. -27 minus 5 is -32. Okay, so what we have now, since we put an input, the answer is an output. So we plug in an x, we get a y. You input an x, it outputs a y. So this is our y value. Because the next question is, what is the corresponding point on the graph? Well, at -3, the y value is -32. There we go. So you input, you evaluate, you simplify, and you get your output. Okay, let's try it again. Number 2, same thing. Evaluate f of 0. So 0 is the input. That's our x value, right? And we're going to take 0 and plug it into that function again above for every x. So when we do that, this is f of 0 equal to 9 times 0 minus 5. 9 times 0 is 0. 0 minus 5 is -5. There we go. There's our input. Our output. Now, the point that it would make if we were to graph it is 0, -5. Okay. Let me see something. Okay, and just to show you, since it's always not algebra, we can actually plug this on a graph. So I can say 9x minus 5, and I can look for the points we just created. So at -3, let's see, we'd have to zoom out a bit. That's -3 and 32. So if I go up here, -3 and -32. That's going to be down here. If I scroll down, we get negative, where are you? Boom, right there. -3, -32. So this just proves that this is a point on the graph. And then we could even do the 0, -5. I'll go here and right there. There it is. 0, -5. So we are finding points on this function, which creates a graph. So again, functions are equations, just stated differently. Okay. Next, it says find x if f of x equals 85. All right, so this one is backwards. So the difference between 3 and the last two is that this is now saying find x. On the last two, we were given x. So now this says find x when f of x equals 85. So what they're giving us now is the output, and they want us to find the input. So this is the output. What they're saying is that y equals 85. So what is x? So using the same function above again, what we're going to do now is take 85 and plug it in for f of x. It's going to replace f of x, not x, f of x. So now when we replace it, we will get 85 equals 9x minus 5. And now all we have to do is solve for x. So I will add 5 over and get 90 equals 9x. Divide by 9, divide by 9, and 10 equals x. There it is. There's our input. So 10 equals x. So again, this one was backwards. We were given an output. Now we had to find an input. And again, what point does this make? This is the point 10, 85. Okay. Number 4. We have evaluate f of a. So again, this is just like number 1 and number 2. They are giving us the input. That's the input. That's the x value. But they gave us a letter. It's okay. You can plug in a letter for x. So you're plugging in a letter for a letter, right? It sounds confusing, and that's because it's meant to be. They want you to be very conceptual. So you're going to substitute a in for every x. It's no different than what we did for number 1 and 2. Number 1 and 2, we plugged in -3, or we plugged in 0 for every x. So number 4, we're going to plug in a for every x. It's the same concept. So using that same function above, f of x equals 9x minus 5. So we do it, and we get f of a equal to 9 times a minus 5. And there's not much we can do here. 9 times a is 9a minus 5. And that's it. There you can't simplify. There's no solving. We just leave it as 9a minus 5. And this one doesn't ask for a point, but if it were a point on the graph, it would be where a and 9a minus 5. Okay, so just a little different just because we plugged in a letter for a letter, right? But it's the same concept. Okay. Now number 5, evaluate f of 2/3. So here we're plugging in a fraction. It's okay. It's going to be the same as number 1, number 2, and number 4. We're going to plug in 2/3 for every x. Okay. So again, there's your input. There's your x value. And now we plug it in. So f of 2/3 is equal to 9 times 2/3 minus 5. Okay, 9 times 2/3. We could do a little side work if you want, right? Side work, 9 times 2/3. This one you can cross cancel or multiply straight across. Either way, you'll get the same answer. Here looks maybe easier just to multiply straight across. So this will give us 18 over 3, which is 6. So 9 times 2/3 becomes 6. And 6 minus 5 gives us 1. There it is. There's the output. I guess I could have put that one up there too, right? Output. Okay, now again, what point does this make on the graph? 2/3 and 1. Okay. Number 6 is going to be just like number 3. So this says find the value of x when f of x equals 0. So again, this one gives us the output first, gives us the y value. It says when y equals 0, what is the value of x? So they want us to plug in 0 for f of x and solve for x. So this means that we're using that same equation, 9x minus 5. This will become 0 equals 9x minus 5. We now solve for x. I add that 5 over. You get 5 equals 9x. And then divide by 9, divide by 9, and 5/9 equals x. There it is. This time that's the input. So we were given an output, we find the input. And what point does this make on our graph? Well, it will be 5/9 and 0. Okay. Again, we can always double check our work just by looking at the graph. So pull that up, put that there. So we found those points already. We did -3, -32, 0, -5. We can look at 10 and 85, and then we could look at, we can't do a and 9a minus 5. That won't be on there. We could do 2/3. Oops. 2/3, comma 1, and 5/9 and 0. And there it is. There's our point, 5/9 and 0. So 5/9 is 0.556. There's our other point, 2/3 and 1. 2/3 is 0.667 and 1. And then our other point, 10 and 85, right up there. So again, what we're doing with these inputs and outputs is we are finding points that are on the equation. Well, we're finding points that are in the graph of this function. There we go. Okay. So just putting visual to what we're doing. Okay. Everybody good so far? Okay. All right. Our next question is how to read a graph using function notation. So they give us a function. They give us the graph of a function, and they just want us to find the pieces. So let me zoom in a bit. We'll just look at this. I can write the questions next to it. Let me pull that up on another screen. One moment. Let's see, 13, 14. Number 9. Oops. That one. Okay, cool. Okay, so now looking at this graph, maybe I zoom in one more time. There we go. Perfect. Let's answer the following question. So question number 1, or 7 as it's labeled, we'll just call it 7, says what is f of 3? F of 3. So now when you're reading values from a graph, the function notation still applies. Remember that this value inside is our x value. It's our input. So now what this question is saying is, okay, when x is 3, look at the graph and find the value of y. So when x is 3, which is right here, when x is 3, what is the value of y? This means we go up to the graph and find that value of y that connects those points. So what we say is that when x is 3, f of 3, or the value of y, is 4. That's it. That's how you read the graph. Okay, we'll try it again. 8. F of -3. Now again, this says when x is -3, so over here, when x is -3, what is your value of y? So we go up to the nearest graph that we see and connect it to the y-axis. And right there, when x is -3, f of -3 is going to be 1. So we're finding these y values, right? This is your y value. I guess I could use the arrow, right? There we go. Okay. And why not, to make it clear, let's just say it's a point. 3, 4, -3, and 1, because those are the points that you see on the graph. Okay. 9 says f of 0. So this says when x is 0, which is right here, what is the value of y? And we go up to the graph and we see that when x is 0, y is also 4. So there's your x value, there's your y value, and we get 0, 4. Okay. F of -4. There we go. So when x is -4, we are right here on the x-axis at -4. When x is -4, we see that the graph crosses there at -4, which means that when x is -4, since it's on the x-axis, y is 0. There's our y value. So that is -4, 0. Okay. Let's see what other questions are. Number 11. This says f of -10. So again, there's x. Now we look at f when x is -10. So that's over here. When x is -10, we go down to the graph. We see our y value there. And we see that when x is -10, y is -6. There's our y value. -10, -6. Okay. And 12, we ask the question backwards now. So 12 is now giving us the output and wants us to find the input. So on 12, this says, for what value of x is f of x equal to 3? So when f of x equals 3, what is the value of x? So now we just reverse the process. Now we look at wherever you see a y value of 3, we look for that x value. So Let me clean up these. So we look at the y value of 3, which is here, and we go out to the graph, and we stop at the nearest part of the graph and go down to the x-axis. We see that that is -1. So when y is 3, x has to be -1. So just working the process backwards, right? Or reversing the process. So here we look at the y value, and then we find the x value. And this would be the point -1, 3. All right. Then 13, same thing. When f of x equals 1, what is the value of x? So when f of x is 1, so when y is 1, so there's 1, what is the value of x? So there's no graph to the right at 1, so we go to the left, and we connect with our graph when x is -3. There it is. And this would be the point -3, 1. Okay. And 14. When f of x equals 0, x, so now we want to know when y is 0. When y is 0, so y is 4 up here, and then negative, and then 3, 2, 1 over here. So what we see is that when y is 0, which is right here on the x-axis, when y is 0, x is -4. So this makes the point -4, 0. There we go. Okay, cool. All right. That was functions and function notation. Everybody good with that page?
Yes, sir.
Okay. All right. Well, that was fast. So let's just jump into the next one. All right, what do we have now? Applications of linear functions. All right, cool. I will, let's see, use the right side to write on. Okay, cool. So let me post these in the chat too. If you need these notes, number 10. That's homework. That's notes. There you go. In the chat. Okay. Now we want to do applications of linear functions. So we're applying actual real life applications to functions. Okay. So number 1, if 1 gallon of gas costs $2.50, how much will it cost to fill a 15-gallon tank? Solve using a proportion, a conversion, a linear function, and explain why they all give the same answer. Okay, so for number 1, we'll call this 1A. We're going to make our proportion. So it says if 1 gallon of gas costs $2.50, so remember with our proportions, I have 1 gallon of gas and it costs $2.50. How much would it cost to fill a 15-gallon tank? So this would be 15 gallons over X amount of money, right? So we can say 250. Yeah, we just leave it like that. That's fine. Okay, now here's our proportion. We can cross multiply to solve for x. So we cross multiply, remember that. Make it neater, right? There we go. And we cross multiply, and x times 1 is x. And you get 15 times 250, which is $37.50. So if that 1 gallon costs $2.50 and you have a 15-gallon tank, it's going to cost you $37.50. Now that's not happening these days. Okay, so that's how we can solve this with a proportion. Next, we can do it with a conversion. So this says we can do a gallons to dollar. So with our conversion, we know that 1 gallon is equal to $250. So if we want to know how much is going to cost to do a 15-gallon tank, this is how we'll set up our conversion. We'll say 15 gallons times, and we're going to convert from gallons to dollars, just like it says. We know that in 1 gallon, there it costs $250. And then when we're doing our conversions, we cancel units. So gallons is canceled. And what we're left with is 15 times 250, which will give us the same answer above, $37.50. Okay, so we have solved it with a proportion. We have solved it with a conversion. Now we want to solve this with a linear function. Okay, so for our linear function, 1c. So one thing we must note about a linear function, so we have it in the form, since we're doing a function, f of x equals mx plus b. So we're going to learn some new definition here. Mx is called the variable cost. So for this problem, if it's 250 per gallon, well, 250 would be your slope, and x would be the amount of gallons you're using. B is called your fixed cost. So this would be if, I guess we could use this for example, if you pull up to the gas station and they charge you a gas station fee. Like, okay, if you want to use our gas, you'll pay $5 first and then you'll fill up. Let's hope that never happens. But that's what fixed cost is. Fixed cost is a cost that's there no matter what. Okay, so this is a small breakdown of how we can create a linear function. And for 1c, we want to solve this problem by using a function. So what we know is that it costs $2.50 per gallon. Now, of course, we're translating English into algebra. So it is 250x. X represents the number of gallons. So this would be the number of gallons. Now for this problem, there is no fixed cost. Again, a fixed cost would be something that's there already. It's a fee before you can go into a theme park. It's a fee before you go maybe to a concert, something like that. Or it's a fee that you pay if you run your own business. It's maybe what you pay your employees, and then you add other costs on top of that. So there's no fixed cost here. So Here, this is 250x, and what we want to know is how much will it cost to fill a 15-gallon tank? So we just plug in 15. F of 15 equals 250 times 15. And just like 1A and 1B above, this would be 3750. So no matter what, if you solve it with a proportion, if you solve it with a conversion, if you solve it with a linear function, we still get the same answer. Now, why do they all give the same answer? Is because, I mean, we're solving for the same thing. We're wanting to know how much gas, or how much would it cost to fill up this 15-gallon tank. So they're all in the same units, they're all in the same conversion. So what we can say is that we are all solving for the same thing, right? Solving for price. We'll just say that. We're solving for the price of this 15-gallon tank. Okay. All right, number 2. It says, look up the cost per credit hour at NVC and at UTSA. Here, I'll save some time. I think I had it, because it took me forever last time to find it. So let me see. It was, there we go. At UTSA, 450, and at NVC, 99. Okay, gonna write those down. So UTSA is 450 per credit, and NVC is 99 per credit. Okay, cool. So now we have the credit costs per hour at MVC and UTSA, and for 2A, it says, how much would it cost to take 12 credit hours at each school? Okay, so let's see. So for 2A, if we go to UTSA and take 12 credit hours, that would be 450 times 12. Which means that 12 hours at UTSA cost $5,400. Then, if we wanted to go to take those same classes at NVC, it would be 99 times 12, and it would only cost us $1,188. I think I know what school we're going to, right?
What's A?
What's that?
Wait. Never mind.
Okay. All right. So it'd be 1,188 at NVC, which is definitely a better deal. Definitely better. Okay. So some things to take in is that one, UTSA, so 2B, UTSA has all those fees, right? UTSA has parking fees, has the gym fee. You now pay for the football team fee and more, right? So these are all fees. So, and the list keeps going. Who knows what other fees you pay at UTSA? So, and that's the same for MVC, but at MVC, I don't think we pay for parking. Or maybe we do, but it's not as much as UTSA. So those would just be fees, and that could be the answer for both. So of course, there's all these little fees that they like to tack on. But still, NVC for the first 2 years would be definitely a better deal. It's like, why don't they give bachelors at community college?
That would be nice.
Right? Okay, cool. All right. I can close this part, sorry. Go. Okay, 3. Mr. Thompson is on a diet. The graph below shows his weight over time. Let me zoom in a little bit more. There we go. Okay, so how much did he weigh when he started the diet? So Mr. Thompson has graphed his weight loss over time. Okay, so looking at the graph, we see that, of course, the y-axis is the weight in pounds, and the x-axis is the number of months. So when Mr. Thompson took on this diet plan, we see that at 0 months, which starts here, at 0 months, Mr. Thompson started out at 260 pounds. So for 3A, we have that. How much did he weigh when he started the diet? So we can say at 0 months, the weight was 260. Okay, so that's the starting weight. Now, in B, it says how much weight did he lose every month? So we want to know what was the trend in his weight loss. So in order to find that, we are going to be looking for the slope. So we want to know what was his weight loss? What was he decreasing at every month? And remember, slope is rise over run. So what we want to do on this graph is actually look for the clearest point possible. So what we're going to do is we start at the beginning weight of 260. So we start at 260, and we're going to go down to 240. So we go down to 240, and let's see if there's a clear point there. So we go down to 240, and we're going to go to the right until we hit an actual point on the graph. So down 240, we go to the right, and we see that what we've done so far is our rise. We've gone down 20 units, and our run, we have gone over 5 months. So for 3B, we are looking at the slope. And again, remember, slope was your rise over run. And we see that we went down 20 units, 260 to 240. And we ran over to the nearest point, the most legible point, right? Which happened to be at 5 months. So you get 20 over 5, which gives us 4. So what this means is that Mr. Thompson was losing 4 pounds per month. So we can also verify that. Let's see if we get the same answer, hopefully. So let's say that we didn't see this point. We go for the next clearest point, and we see that the other clearest point is there. So to get to that point, we would go down 20, 40, And we go all the way to the right until we get to that point. So in this case, our rise was 40. So we went 20 and 40. So it was 40 units over 10. So we stop at the 10 months. And 40 over 10 is still 4. So either way we get it, we're reading the graph, we're looking at the slope because this is determining how much weight Mr. Thompson's losing every month. So we know that he's losing 4 pounds per month. Okay. Awesome. So then question C, estimate how long he has to be on the diet to weigh 198 pounds. So let's see, it says estimate, so we don't have to be perfect. So let's look at our graph again. And let's find 198. We'll just put it right at 200. So let's go to the right. And we see that 198 is not on the graph. But what we do know is the last point we found. This point is at 10 months. And at 10 months, he's at 220 pounds. So now, if he's losing 4 pounds per month, well, in 11 months, he'll be at 216. So 11 months, 216, 12 months, 212, 13 months, be at 208. So all I'm doing here is subtracting 4 every time because he is losing 4 pounds per month. And then in 14 months, he'll be at 204, 15 months, 200. And we could even do one more. We could say 16 months, he'll be at 196. So in 15, 16 months, Mr. Thompson will be at 198 pounds. So for 3C, we'll say in about 15 to 16 months, I think that's all we have to say, right? So how long will he have to be on this diet to weigh 198 pounds? 15 to 16 months. Okay. Okay. Everybody good so far? Okay. Okay. Number 4. Kara uses the linear model f of x equals 20,000 plus 0.3x to predict her total salary from achieving total sales of x. Interpret the slope and the y-intercept in terms of her salary and sales. Okay, so this goes back to the function notation I provided above. So, oh, come on, scroll back. So remember that whenever you're given this function notation, mx is your variable cost and b is your fixed cost. So that's what we're going to be using to interpret number 4. So I'll rewrite it again. So if we are given f of x equals mx plus b. Remember that mx is the variable cost. Or in this case, it says to predict her total salary from achieving total sales of X. So it could be total cost, it could be total profit, it could be total salary, whatever you want to name it, just as long as it's changing. That's why it's a variable, right? Okay. And B is your fixed cost. It's the number that won't change at all. So this is your fixed cost, or maybe your fixed profit, your fixed salary. It all depends on the wording of the problem. Okay, so looking at the function given above, it's written as f of x equals 20,000 plus 0.3x, which is fine. It's just written opposite, right? So over here is your mx and over here is your b value. So we can label those as such. This is the b value and this is your mx. Okay, so reading this over again, it says she uses this model to predict her total salary from achieving total sales of X. Interpret the slope and the y-intercept in terms of her salary and sales. Okay, so let's say that Kara makes no sales. This means that X would be 0. So if Kara didn't make any sales, she would still make a salary of $20,000. So this is why $20,000 is going to be our fixed, we're going to call it our fixed salary. So B, which is the y-intercept, is also known as the fixed salary. Yeah. If she makes no sales at all, she's just hanging out, she's going to make a $20,000 salary no matter what. So that is her fixed salary. But now, let's say that she loves making sales. She knows she's going to get $20,000, but why not add on to that? So this is the next part. It's her variable salary, right? So it's going to be whatever sales she makes is going to add that on top of her salary. So this mx, this is our slope, and it represents the number of sales she's going to make. So this is going to be the number of sales and the amount she gets multiplied by sales. So if she sells $10,000 in sales, she multiplies that by 0.3 and we add that on to the $20,000 she's going to make. So that's it. That's the interpretation. So slope is your mx. She's going to get 0.3 of every sale she makes, and that's going to be added on to her salary of $20,000. Okay, so that is just interpreting that function. Everybody good with this page? Okay. All right. Next. Joe has a part-time job caring for and walking dogs. He estimates that his annual insurance, etc., is $420. On average, he spends $4.50 on gasoline per visit. He charges $15 per visit. Note that this is an annual cost function. So Joe wants to know how much he's spending to run his dog carrying dog walking business. That's why we call this an annual cost function. And for our cost function, I'm just going to rewrite it again. It's going to be in the form of f of x equals mx plus b, where mx, now since this is a cost function, mx is your variable cost, and b is your fixed cost. And like I said, we label these differently depending on the problem we're given. The last one was a salary problem. So it was variable salary, fixed salary. Okay. Now for A, it says explain how to find his total cost, his overall cost. So what we're going to be doing is creating his cost function. So in 5A, we're going to set up his cost function, f of x, and we're going to look at the problem again. We're going to look at something that has a variable and something that is fixed, and we're only looking at cost. So this says he estimates that his annual insurance is $420. So what this means is that no matter what he does, if he quits caring for dogs, if he stops working, if he goes on vacation, no matter what, he is going to pay $420 in insurance annually. So this is going to be considered his fixed cost. So we're going to put that down first, 420, because no matter what he does, this is the amount he pays. So we have found the fixed cost. Now, plus, we're going to look for that variable cost. What's costing him to do this job? So the next piece says, on average, he spends $4.50 on gasoline per visit. $4.50 on gasoline per visit. So this is what he spends to go do his job. So this is another cost. And it's $4.50 per visit. So we don't know how many visits he does. So to represent that, we say 4.5x. This is the variable cost. And now something we threw in there just to throw everybody off was he charges $15 per visit. That wouldn't be considered a cost. That would be his profit. That's what he's actually making, or his revenue. So we do not include this in the function because we're only looking at the annual cost. So this equation represents what it costs him to run this dog business. So there it is. 420 plus 4.5x. Okay. So now, since it's an equation and since it's a function, we want to compute it. So on 5B, it says fill in the table for the values below. So we're going to take 0, 1, 2, 3, and 4. We're going to plug those all in for x and see what it costs him every time he does a visit. Okay, so this is going to be 5B. Okay, so to make a table, I'm going to show you how to use Desmos. So zoom in, that zoomed out too much. Okay, so let me clear everything that's here. So to calculate these values, yeah, it's not crazy difficult, but if you want to learn how to use Desmos, what we're going to do is type this function in. I'm going to say 420 plus 4.5x. Now, what I'm going to do is hit this little gear icon right above where you type the function in. You hit this gear icon. and you're going to see a little button here that says convert to table. We're going to do convert to table, and it creates an XY chart for us, just like the one we have to fill in over there. And it lets us plug in the numbers we need to. So for us, we need to plug in 0, 1, 2, 3, 4. So I'm going to type those in. 0, 1, 2, 3, 4. There we go. And now just fill in our table over here. If he does 0 visits, let's say he's taking vacation for the year, he is still going to pay $420 in insurance. But now he does 1 visit, and since he has to pay that gas, it's going to cost him $424.50. 2 visits, $429. 3 visits, $433.5, and 4 visits, $438. So every time he goes out to take care of somebody's dogs, of course, it's costing him more in gas, but you also think how much he's charging to do this. So it kind of balancing it out. Okay. But I just want to show you how to create an XY chart in Desmos. I'll run it back one more time. You just type in the function 420 plus 4.5x. Click on this gear icon, hit the little table button, and type in the numbers that you need to. Not bad. Okay.
Oh, wait, could you wait for 1 second? I'm still trying to copy this.
I'm not done yet, so you're good. Okay. So on C, it says, suppose his budget is $1,000. How many visits could he make annually? So now it's saying that Joe has $1,000 to spend. So it's giving us the total cost. So for 5C, it's saying if his total cost, his budget is $1,000, how many visits could he make annually? So remember, visits here are represented by X. So it says if f of X is 1,000, what is the value of X? So this is just like the function notation we were doing on the last set of notes. It just wants to know how many visits could he make if he has $1,000 in his budget. So what we're going to do is take 1,000, you plug it in for f of X, and solve for X. So we get 1,000 equal to 420 plus 4.5x, and then we're going to subtract 420 minus 420 minus 420. Gives me 580 equal to 4.5x. Then you divide by 4.5. And if he has $1,000 in his part-time dog business, he can make up to 128.89 visits. But of course, he can't make 0.89 of a visit. So let's round that up to 129 visits. Okay. Everyone good?
Yeah.
Okay. Okay. Number 6, it says in meteorology, the temperature is related to the altitude by the formula T of H equals negative 3.5 H plus 58.6, where H is in thousands of feet and T is the temperature in degrees Fahrenheit. Identify and interpret the slope of this equation, of this function. Okay, so looking at the function given, this is T of H equals negative 3.5 H plus 58.6. So your negative 3.5 H is going to be your slope. And what it represents in this problem is, reading it over again, it says temperature is related to altitude by the formula where H is in thousands of feet and T is the temperature in degrees Fahrenheit. So since this slope is negative, this means that the higher you go in feet, the more the temperature is going to decrease. So it just makes sense. Whenever you see those mountain climbers, the higher they get, the colder it gets, right? So for A, we know that the slope is negative 3.5. I'll put the H on there. And what it means is that as height increases, temperature decreases. Okay. So that's for A. Now for B, it says, what should the temperature be if the height is 12,000 feet? So what we want to do here, they're giving us the input. They're saying plug in 12,000 and find the temperature. Okay, so something to note here is that H is in thousands of feet already. So for B, they're telling us that X is 12,000, but since H is already in those units, all we have to do is plug in 12 because it's already in thousands. So what we're going to do, oh, sorry, not X. I shouldn't say X. In this problem, it is H for height. So H is negative 12. Not negative 12, it is 12. H is 12 in the thousands. Okay, so all we have to do here is say T of 12. We take 12, we plug it into H into this function. So T of 12 gives me negative 3.5 times 12 plus 58.6. And let's calculate. Let's see. Negative 3.5 times 12 is negative 42 plus 58.6. And if we climb 12,000 feet, the temperature is going to be 16.6 degrees Fahrenheit. So at 12,000 feet, we're at 16.6 degrees Fahrenheit. Okay. Now for C, it says at what height will the temperature be 32 degrees Fahrenheit? So now this one is, again, giving us the output and we need to find the input. So they want to know, how high do you have to climb to be at 32 degrees? So for C, this says T of H, at some height, T of H is going to be 32 degrees Fahrenheit. What height will that be at? So our goal here is to solve for H. So we're going to take 32 degrees and plug it in for T of H and solve for H. So this means we'll have 32 equal to negative 3.5H plus 58.6. I'm going to subtract that 58.6 to the left. So you'll have 32 minus 58.6. This will give me negative 26.6 equal to negative 3.5H. And then we divide by negative 3.5. And here, height would be 7.6. But remember, height is in the thousands. So we can't say at 7.6 feet, the temperature would be 32 degrees. That doesn't make sense, right? So what we have to do is multiply this answer by 1,000. And we will get that in order for the temperature to be 32 degrees Fahrenheit, the height must be 7,600 feet. So at 7,600 feet, you're at 32 degrees. Okay. Okay. Number 7. In 1990, Americans ate at restaurants an average of 143 times. By the year 2000, this had reached 170 meals out a year. If there is constant growth, how many meals a year do you expect us to eat in 2030? So we want to know how many times are we going to go out to eat by the year 2030? Okay, so what we want to do here is, since there's a constant growth, is we want to find the slope. We want to find the change in how many meals are being eaten at a restaurant in America, right? So constant growth is just fancy for slope. So remember from last week, we learned that slope was given by m equals y2 minus y1 over x2 minus x1. And in order to find slope, we have to be given 2 points, which we have. Our 2 points here are that in 1990, Americans went to restaurants 143 times. So there's our first point. In 1990, Americans ate at restaurants 143 times. Now, my second point is that in the year 2000, those numbers reached 170 meals. So this would be 2,170 meals. Now, there's my 2 points. And since there's a constant growth in the way these, in the change of meals being eaten, we can find the slope between those 2 points. So let's go ahead and find the slope. We'll have m equals, and if I label everything, there's x1, y1, x2, y2, and my y2 is 170. My y1 is 143 over x2, which is 2000, minus x1, which is 1990. Okay, so we have 170 minus 143, which gives me 27, over 2000 minus 1990, which is 10. 27 divided by 10 is 2.7. So what we're saying with this slope is that from 1990 to 2000, Americans were eating 2.7 times more meals every year. They're eating 2.7 times more meals every year. Now, what we want to know is how many meals we're going to eat in the year 2030. All right, so this means that from 2000 to 2030, 30 years have passed. So let me see. Would we do that plus 143? I think so. Let me see. An average of 143. By that time, they reached 170. So 2.7 every year. Yeah, so how much are we expected to eat out in 2030? Yeah, so I think we do, let me see. Yeah, that'll work. Okay, so from 2000 to 2030, there are 30 years, right? So we want to know in these 30 years, how many more meals are going to be eaten? So what we do is first, you do 2030 minus 2000, which gives us 30. We have to figure out how many more meals are eaten. Well, what we know is that every year, 2.7 more meals are eaten. So we take 30 and multiply it by 2.7. And 30 times 2.7 gives me 81. So what we know now is that 81 more meals will be eaten in the year 2030. So what we do with this information now is that we know that in the year 2000, there were 170 meals. And in 2030, we're going to eat 81 more meals, which means that the average number of times we're going to go to a restaurant is going to be 170 plus 81. And we, in 2030, will eat 251 meals at a restaurant.
1 second.
So 170 meals were eaten in 2000, and in 30 years, we're going to eat 81 more meals on top of that. So 251 meals is what we will eat in the year 2030. That's a lot of McDonald's. Okay, number 8. This says, give an example of a real life situation with a variable cost and a fixed cost. What cost you money? Everything, right? So maybe, what could I say? I'll start, right? One good example of a function with a variable cost and a fixed cost. Let's say my fixed cost, well, it has to be like an annual fixed cost, right? Well, if you add it all up, it is. Let's say my fixed cost is a house payment. Actually, no, this will be my variable cost because I make a house payment every month, right? So that's variable cost and plus insurance on everything, right? So that is a fixed cost. So at the end of the year, my escrow, whatever escrow is, I still don't know. I read about it, but it's still confusing. Goes to my insurance, goes to the property taxes. So that is a fixed cost no matter what. So that's a good life example, right? Maybe another one. Let's see. I'm just trying to think of bills, right? There's nothing fun. There's no fun answer for this other than bills, right? Let's say, well, we could use the gas one, but we already have it in our notes. Maybe tune-ups. We could talk about cars, right? So we could say mechanical costs. How about this? Mechanical costs are a fixed cost. That would be fixed. And to go get your car fixed, you spend gas. So that could be variable. There we go. All right, that's good enough, right? I'm sure we could think of other examples, but don't want to bring up bills too much, right? Okay. Number 9, a bacteria population doubles every minute. Explain why this population growth cannot be modeled using a linear equation. So remember that a linear model, right? A linear equation or function is given as y equals mx plus b, or f of x equals mx plus b. And remember, since it's linear, it is just the graph of a line. That's it. It's just the graph of a line. Well, for a bacteria population, if it doubles every minute, it is no longer linear. You can't express that situation being linear. Since you are doubling every minute, you are exponentially growing. So when your population doubles every minute, it is exponential. So this is why we cannot model a population growth by linear models. So population, right? Population growth is exponential. So when we say exponential, I mean a to the power of x. And if you have an exponential function, exponentials look like this. They curve. Or if the population is decreasing, they go the other way. They decrease. So again, since this population's doubling every minute, that's not linear, right? It has to be represented exponentially. So this is why we can't represent that by a linear model. Okay. And number 10, how much water should be added to 1 quart 3% milk to result in a 2% solution? Oh, I guess we just wanted to refresh on mixtures again. Oh, all right. This shouldn't be too bad. So remember our mixtures formula was amount 1 times the percent plus amount 2 times the percent equal to the total amount times the percent. Okay, so for 10, it says how much water should be added to 1 quart of 3% milk to result in a 2% solution. All right, so how much water should be added to 1 quart of 3% milk? So one thing we know is that we're doing 1 quart of 3% milk. So that would be 1 times 3%, which would be 0.03. The other thing we don't know is that we want to know how much water we should add. So we're going to do X amount of water, and the solution of water is 0. And then the last thing we don't know is how much the total solution is, the total amount is. So that's going to be X, but we want it to result in a 2% solution. So this will be X times 0.02. Okay, well, 1 times 0.03 is 0.03. X times 0 is 0. And X times 0.02 is 0.02X. Now, we just divide by 0.02. And let me see, 0.03 over 0.02 means we get 1.5 equal to X. So in order to create a 2% solution, we need to add 1.5 quarts of water. So 1.5 quarts of water. And then it says how many quarts of total solution would this make? And that would make 1.5 plus 1. It would be 2.5 quarts of total solution. Okay, cool. All right, so that was just a refresher on mixtures. Don't worry, you won't see mixtures on this second exam, but I guess they just had to throw this in there. Okay. That was applications of functions. And I think that's it for the day. Let me see. Yeah, that was function notation, application, linear functions. So we are done. If you have questions, stick around. If not, see you on Wednesday. Get your exam done. And that's it.